we know the center here, and there's a central angle measured in radians, right? Well, its intercepted arc length is S equals, suppose this is the intercepted arc length, S equals radius times theta. Yeah. Here, suppose our theta has the reading measure. Let's say it is a T. Suppose that is the measure in radians of this angle. So if it's T, that means whatever that measure is, we use that T radians times radius to get the arc length. But when the radius is 1, you see the arc length will be the same as, if suppose the radius is 1, the arc length will have the same numerical value as the measure of the angle. So simply speaking, if we have a unit circle, which means the circle has a radius 1. So if radius is 1, then radius times the measure of the angle equals the arc length. So the intercepted arc length has the same value as the central angle. So that simplifies the matter, because whatever this arc length, it is the same as the angle measure in radians. So that's the same number. Suppose we have a positive angle in radians, then this arc length, we can just adopt the same number as this positive. Suppose you have a T, because if this is the initial side, and then you generate a negative angle in radians, and then this, we can also use the same number. So here we continue to look at the trigonometric function values. Suppose we pick a point. We want to find the sine and cosine of t. So if we have t, we want to find sine t and cosine t. Assuming this is the center, and then we place the angle in the standard position, right? This is the initial side, and then the sine t, according to our practice, we pick a point which is on the terminal side of the angle, and sine t is defined by y over radius. So the radius is 1, so then the sine t is simply y. Because y over radius is 1, so it is y. The cosine t is defined to be the x coordinate of the point on the terminal side of the angle. So x over radius. Because r, so let's just look at this. Which one is y? This is y, right? Using this point. So that is the y, this is the x. So we see how to use that point. So y over r x over r are respectively sine, cosine. So x over r will be just simply x because our r is 1, the radius. So using a unit circle, we can immediately recognize the sine value of t is simply the y coordinate. And cosine value of t is simply the x coordinate of the point on the unit circle. So it is also true for the case when t is negative. If we just simply pick a point, right? This is a point on the terminal side, and also it is on the unit circle. So if we choose the point to be the point on the unit circle of the terminal side of the angle, then the y coordinate, the y value is simply this, the length of this line segment. And x will be this portion. So the r is always 1. So y over r, which is y. So the sine value, the y is just the sine value, sine of the t. And the x over r is cosine, right? R is 1, so x is the cosine value of t. So we can see that when you pick a point that is on the unit circle corresponding to this t, and xy coordinates are just simply cosine and sine values of the t. So this result is simply by our definition of sine, cosine. So we just, let's take a closer look. So the cosine t, which is the x coordinate of the point, right? Sine t is the y coordinate of that point on the terminal side of t, also on the unit circle, right? That's the point we picked. So with the sine, cosine, then we can also calculate the tangent, right? So y over x will be the tangent. And also we know this reciprocal property. So if we get sine is y, then reciprocal of sine will be cosecant. So which is 1 over y. So the formula is becoming simple because whenever it is r over y becomes 1 over y due to the fact that radius is 1, right? So whenever this, by the definition, secant is r over x, the radius is 1, so 1 over x is the secant. So, but the cotangent, we still have to use x over y for the tangent and cotangent. So y over x for tangent, x over y for cotangent. But whenever the formula involves r, then it becomes 1. So that is a simplified way to calculate trigonometric function values using the point of the terminal side of the angle that lies on the unit circle. So we want to use for this angle, just not only it is a point on the terminal side, it is a point on the unit circle, right? That simplifies our calculation of the trigonometric function value at this t. So certainly we know that to calculate the trigonometric function value, whichever point on terminal side can be used, right? You can choose to use any point, but this point does have convenience. And also it shows that on the unit circle and this measure, the reading measure for the angle is the same number for the arc length intercepted by the angle. So that means whenever you talk about sine t, which is just the sine of the arc length as well. So whenever we are using the unit circle, so the s is the same as t. So sine s, if we use consider this t is the length of the arc. So if you view this x as a cosine t, same as cosine the arc length, right? Cosine s. Because s and t are the same. And the y is the sine t. And also it can be viewed as the sine of the arc length. So sine, cosine can be viewed as functions of either t or s, they're the same quantity. Now we evaluate the 6 trigonometric functions at this t. So this t is 3 pi over 2. We can just simply consider the unit circle 3 pi over 2. Where is the point, right? We need to find the point corresponding to 3 pi over 2. So let's go to this picture, just try to identify that point. So if we just look at pi over 2, that's half of pi, then you get this. That's pi over 2. But you continue, this is at another pi over 2, right? Get here. And 3 pi over 2, that's 3 of these. So then this is, suppose this is our standard position angle. So actually you go all the way here. So we just see this angle 3 pi over 2. So this that means we need our point is this one. The P, this is the initial side, and it goes 3 pi over 2, and this is the terminal side. And the P, what is the X value? X has to be 0 because it is on the Y x-axis. Yeah. Then the Y is -1. It's on the unit circle. So 0, -1. So this is the point. When we have X and Y, so this is X, which is 0, Y is -1, then R is always 1 because R radius is 1. So, and we know that sine X, which is Y, immediately we can see sine of 3 pi over 2 must be -1. Cosine 3 pi over 2 must be 0 because the X value is the cosine value. And this Y coordinate is the sine value. Okay, so we have sine cosine immediately. So after we have sine cosine, then we continue to get tangent cotangent. So let's say, what is the tangent of the 3 pi over 2? Tangent is y over x, undefined, right? This is y, which is -1. Was there 0? That there's undefined. And what is the cotangent? 3 pi over 2. Cotangent is x over y, so 0 over -1, which is 0, so that's a 0. Then still two more functions. That is secant. Secant 3 pi over 2. Secant. Then we need to use r over x. R is 1, the unit circle, over x. X is 0, undefined. You see, whenever the cosine is defined and has a value of 0, the secant must be undefined, right? We notice because of the 0 in the denominator. So also we know sine, secant and cosine functions are reciprocal to each other when they're both defined. So if one is 0, the other is undefined. So secant is undefined. And one more, cosecant. Cosecant 3 pi over 2, which is r over y. Y is -1, so the ratio is -1. So that is the cosecant. So now we have found sine, which is the y value, y coordinate, cosine, and tangent, which is undefined, cotangent, secant, undefined, cosecant. So this is one application to show how we use the point on the unit circle to evaluate 6 trigonometric function values at a certain angle. Now there are some properties we can conveniently notice. For this, let's look at pictures. We can see that cosine function is even by looking at this picture. Just intuitively, we get that property, but of course, we can prove it using definition, right? That's more strict proof. But now let's just get this intuitive visual approach to see a cosine function as an even function. So suppose this is the t, the positive t, okay, I put it in blue, that's the t. And the negative t, I put in the right. So you see, t is a positive number, right? So then suppose here going counterclockwise, then we have a positive measure t. And when you go clockwise, that's a negative measure t. And we pick the point corresponding the positive end, that is the p here. And we pick a point on the unit circle. Okay, that is the point on the unit circle corresponding to the negative t. So we're going to see this is the x coordinate, right? For this point, this is the x coordinate, which is the cosine of negative t. This is the y coordinate of this point, which is equal to sine of negative t. That's something we know already. by the previous discussion. And then this first coordinate, which is x coordinate of P, which is the same as cosine T. And the y coordinate of the point is the same as the sine T. Now we want to see that actually because of the symmetric, right? T negative T is for this quantity, this symmetric property, then we see the two right triangles, and this y, which is the same as the sine T, and the other, and this y, which is sine negative T. Are they the same? No, because they are opposite, right? Sine negative T is a negative quantity. Here, this y is negative. The other y is positive. So we just, let's just use sine T and sine negative T to show that. You see sine negative T, this is a quantity that's negative. Sine T is positive. So that means the sine function is odd because sine negative T and sine T are not equal. So the sine T is a positive here, but sine negative T is negative. So they differ by a sign. Okay, but x coordinate, this cosine T, which is this cosine negative T is also that same x, right? Also this. So that means the cosine negative T, which is that x coordinate, which is this is both, this green is both cosine negative T and also cosine positive T. That's the x coordinate of the point P and P bar. So this is to show that cosine positive T and cosine negative T are the same, are equal, because this yeah, in the graphical representation, we see that. Yeah, so that is quickly, if we just clean up, don't worry about all the notations. We just see that where is the cosine T? Cosine T is the x coordinate of the P, right? So then you will see it in green. Yeah, x coordinate. And what is cosine negative T? That's also this x coordinate of this point, P bar, which is also the green part. So they're the same. But the sine T and sine negative T showing sine T will be this portion. Sine negative T will be the right portion. So they are opposite quantities. And this sine negative T is the opposite of sine T. So they are not equal. But cosine negative T is equal to cosine T. This shows cosine is an even function because it's true for any T, right? It's true for any arbitrary T. And we notice the cosine is even, but sine function is odd. This is another identity, although it's not a strict proof. So we can visualize this property on a unit circle. So if we know that, then how about secant? Secant is, because cosine is even, secant is also even function because secant is the reciprocal of cosine, right? When cosine negative t is the same as cosine t, then we can verify that secant is even as well, just like a cosine function. And the sine function is odd. The cosecant is also odd because the cosecant at negative t is just a reciprocal of sine at negative t. So because sine is odd, then we can apply that property and end up with a negative cosecant t. So cosecant negative t is negative cosecant t. So cosecant is odd. When sine function is odd, cosecant is odd. And similarly, we use quotient property. We can show that tangent function is odd. This is true for n and t. So tangent negative t is negative tangent t. That shows tangent function is odd. How do we prove it? We can use the even and odd property of sine cosine. And then cotangent negative t is negative cotangent t. So that means cotangent is also odd. How do we prove it? We're using what we already know. That means cotangent is the ratio of the cosine and sine, right? So cotangent, we can prove, we rewrite this cotangent and negative t. And then using the even and odd property of cosine and sine, then, yeah, cosine is even. So cosine negative t is cosine positive t. They are same. Sine is odd. Sine negative t is negative sine t. So then when we divide cosine by sine t, we get cotangent. So we get, so this is some algebraic um, and also some analysis we can practice to understand. So anyway, so how many even functions among the 6 trigonometric functions? Only cosine and secant are even functions. All the rest are odd functions. So the only even functions, cosine and secant. Secant negative t is secant t, right? So these two are are even functions, and the other 4 trigonometric functions are odd functions. And they are very useful because if you remember there which one is even, which one is odd. For example, the sine at negative pi over 4, because the sine is odd, immediately you can put the negative outside of the sine function. So it's a negative sine of pi over 4. So this pi over 4, we know it's a special angle. So sine pi over 4, we know it is square root of 2 over 2. Then with the negative sign here, so we get the value to be negative. So this odd function, so then you can reduce this problem to just the problem of sine pi over 4. So you then take care of the negative later. And secant function is even. It is an even function. Sine of a negative is same as the sine of the positive of this angle. So sine negative pi over 6 is the same as sine pi over 6. So pi over 6, you know, it's a 30-degree angle, right? 30-degree angle. So then we know the secant 30-degree is this. So using even odd property can immediately reduce the expression to simpler looking expressions. And here's another one, cotangent negative is, because cotangent function is odd, so it is negative cotangent pi over 3. Pi over 3, remember it's a 60-degree, right, angle. So cotangent pi over 3. So cotangent 60 is this number, and with that negative sign here. And that's the final answer.